All right, I think we can move on with our program for today. Maybe some people will trickle in as we speak, but let's respect our speaker that's on time. So it's my pleasure to present Barrett Ames from BotBuilt. Barrett Ames is a co-founder of BotBuilt, a startup that uses robotics, AI, and computer vision to build houses. Wow. BotBuilt software analyzes building plans and its robots build exact components, enabling house and frames to be assembled on-site in hours. Dr. Ames completed his PhD at Duke University and has a bachelor in computer science from Cornell. He has previously worked at TRACLabs and Realtime Robotics. Help me welcome Barrett.
Thank you, and good morning, everyone. My name is Barrett Ames. I'm the CTO and co-founder of BotBuilt. First, I'd like to thank Neil for the invitation and for organizing, and also to say this is the first time I've given this talk, so please, questions are welcome. I want to know where the rough spots are. So first, I'll give you an idea of what BotBuilt is doing. And the idea is to help kind of give you a flavor of the objective function and constraints that we're operating under. So what's the big societal problem we're tackling? It's the housing crisis. We're short roughly 5.5 million homes in the US. It's not just a US problem. Housing across the world is quite difficult to find. And that's basically because of a labor shortage. By 2030, we expect to be short roughly 3 million construction workers. And that's due to a bunch of reasons. The biggest driving factor right now is that we expect half of the labor force to retire in the next decade. It's also a ridiculously dirty, dull, and dangerous job. Our CEO, Brent, was in Special Forces for 7 years, running around Afghanistan. The worst year of the Afghan war for the US service member, 35 people died. Last year in framing and construction, 350 people died. So by anyone's definition, that's unacceptable. Because they're here to build our homes, right? They're not off fighting a war somewhere. It's dull, as you'll see, there are many repetitive aspects of it, and it's dirty. If you've ever been on a construction site, like, it's defined by dirt. So what's our process for handling this problem at a very high level? Builders come to us, they say, please help us build a home. We have a chunk of software that does all sorts of interesting stuff. That's mostly what I'll be talking about. It then puts the output of that software onto the robots. The robots execute. What do they actually build? They build chunks of framing components, right? So if you think about your house as one big framing component, we break it down into chunks and build each of those individual chunks. We stack them up on the back of a truck and ship them out, right? So we're not too on-site construction robotics yet. We're doing this in a friendly environment in a warehouse. And then once those shipping components, or once the framing components are shipped and at the job site, the big win is that it takes the framing labor's job from a 2-week arduous task to they can finish a house in under 4 hours. So there's a massive improvement in efficiency there. But let's actually talk about the interesting technical bits, right? So first and foremost, every builder comes to us with a floor plan. That, as you and I might expect, is a technical document that defines the location, size of doors, windows, walls, but it's not actually a technical document. It's more like a vague agreement between the architect and the carpenter. The best example I have is recently we finished a house, and the design for it, when we ingested it all into the system, the exterior of the house was not a closed polygon. There were holes all over the exterior of the house, and it wasn't for windows. And so we went and we asked the architect, like, what's up with this design? And they said, well, we just didn't want to deal with fractions. So they just rounded everything. And that, so I want it to be a technical document, but in reality, it requires a bunch of intelligence to parse what is actually intended here. And there's some, kind of intercultural aspect as well. So once we have that floor plan, then we develop what we call a framing plan. This is basically where does every single piece of lumber need to go? Where does every nail need to go? How do we size it so that it works with the doors and windows that you want in your house? That gives us kind of the goal for task and motion planning. We'll talk about that more later, but it's the input to what we call the framing schedule. And this chunk is where task and motion planning lives at BotBuilt, right? It's where we're thinking geometrically and logically about how to take that panel, that chunk of framing, and actually physically do it. And then we put it on the robots, like you see here. This is our second pair of robots, and we build a frame for somebody's house. So like I was saying before, the goal for the scheduler is this framing plan, right? So we will take a chunk of this, usually somewhere between 4 and 8 feet, and use that as our goal. And we do that by specifying a whole bunch of PDDL predicates for, where should all of this lumber go, where should all of the nails go. That's how we define our goal state. Then we have to include the environment. There's a whole bunch of predicates from the robot environment that we need to include. So here I'm trying to illustrate basically the environment that the robots are working in, right? So on the far side, you can see we're just picking up out of a stack of lumber. It goes into this 80-20 aluminum structure in the back. That's where it gets shifted around, so that way we can cut it down to size. Then we have a whole bunch of end effectors, which we just refer to as tools that sit in our tool belt because it's construction, and we pick up various tools for various jobs. Next, in order to actually, take the task and motion planning framework and use it, we have to develop a bunch of behaviors. And all of those behaviors are developed by hand. So here's a kind of a stylized image of one of our behaviors, which is picking up and putting down a piece of lumber that's already been cut, right? So you see the beginnings of a wall down here at the bottom. We're going to place it down there. We have, like I was mentioning, several behaviors that we have to encode. And there are things that we manually have to encode. For example, to complete this task, you have to be holding that tool. There are other aspects of the problem that I didn't want to manually encode because it would be rather arduous, which is the geometric constraints. So here what you can see is the tool is holding a piece of lumber, and for this particular panel, if we just go straight down, our nail gun on the right is going to run into that stud. That's a failure case, right? The robot's going to stop itself, or worse, something's going to break. And so there's two ways to fix it, right? We can either turn the nail gun around and place it that way, or we can change the order of how the studs are placed. And that's, that would be how you would get around that problem. But how do you think about it when you're doing your PDDL, when you're doing your task planning? How do you come up with those geometric preconditions? We do it in simulation, right? So here's BotBuilt, here's our end effector, here's a piece of lumber, and we just simulate all of the pieces of lumber and all of the nails when we're, for a particular action, right? So this particular action is placing a piece of lumber there. We're going to go through and simulate the locations and size, extent of all the other pieces of lumber. If any of them intersect, we're going to know the precondition for this action, that lumber can't be there, right? The result of that is this madness, right? Like you get your symbolic action that has hundreds of predicates, one effect, some cost. We shove that into fast downward, and what we get out is a plan, a sequence of behaviors that we're going to execute on the robots. And what's that look like? Let's see. So here's the output. Pick up a piece of lumber out of the bunk, move it over to our saw table, move it so that way it's going to be in the right position to cut it. We cut it. Yeah, we put a 16-inch saw blade on a robot. It was fun. Pick it up and then put it on the table. Do that a bunch of times and nail it in, and you've built a house. So this is actually one of our houses. It was one of our first houses that we did in Arkansas. We've done 9 houses total so far. Oops. So next, I wanted to talk about a few things that we learned while we were building out this system. They're not, these are all, everything I'm going to be talking about is very heuristic. It's things that we've found have worked well, and by well I mean have failed us in less than 5% of cases. I don't know of a theoretical underpinning for any of these. That's why I'm bringing them here. So the first and foremost is the tool heuristic, right? Most of task and motion planning, you're thinking about the tool and the robot. We actually just do task and motion planning with just the tool. We don't consider robot kinematics. We don't consider robot collisions. It's almost always worked. I think that's pretty interesting. I think there's a huge benefit there, which is that it reduces the dimension of the problem. The downside is, of course, it doesn't consider the robot at all. So what if the robot runs into something? And I think generally there's a few mitigating circumstances that allow us to get away with this. One, it's a tabletop environment that we're operating in. And two, we chose our robot to be a 7 degree of freedom system, so that way we always have a lot of solutions in kind of our workspace area. But I'm still interested, like, when is this heuristic invalid, right? I don't know yet, but I think that's an interesting question that we should investigate. The other thing that we discovered is that prototypical motions are super useful for validating behaviors, right? We don't do task and motion planning and take that motion from task and motion planning and then go and execute it. No, it's like Jeanette was saying earlier, we use motion planning to kind of validate behaviors, and then those behaviors go and execute. And that's, to me, it's interesting, and I don't know where that line or what separates a good prototypical motion from a bad prototypical motion, right? I have a bunch of these behaviors. The behaviors were developed by hand, but I can just go and do motion planning somewhere else, essentially mostly divorced from the actual motion plan or controller that I'm going to do, and it still works, right? Like, that's kind of crazy. The other interesting thing that came out of it is that task and motion planning is useful for humans. Building a panel is actually, it requires a few thoughts, a few steps ahead when you're thinking about things, right? So we can give the schedule that the robots use to humans, and we actually save them hours of work. Because when you mess up, when you build a panel the wrong way and then you go to put your nail gun in and it doesn't fit, you gotta tear it apart. And that's a bunch of lost time. So I just kind of threw that in there as an interesting, task and motion planning works outside of robots. It also works for humans. And then a few challenges that I wanted to bring up. When I was thinking of these, I was thinking of humans. But generally, I think they could be used as sources of feedback for machine learning or to help humans in general. Like I said before, this is that crazy PDDL thing that comes out of our auto-generated PDDL. I kind of understand this, and I wrote the code. Luke is the other guy here from BotBuilt. He's had the fun task of picking up this code after I've written it. It's like, you know, you gotta somehow transfer like the symbol grounding that's in my head into his head. Or if we could just visualize those groundings better, that would be great. Another thing is, you know, your fast downward planner, whatever your logical planner is gonna fail. And so far, every time it's failed for us, it's because we misspecified a logical state, right? One of our preconditions or effects was just improperly specified. It actually hasn't failed because of motion planning. And, you know, this file in particular is like 3,500 lines long. It'd be cool if it could say not just, hey, I failed, but like these two things are what's in contention, right? Kind of an unsatisfiability core. And that makes a lot of sense when you're only talking about, you know, Boolean things, but if we start introducing motion planning, can we think about this is the object that's causing the failure, or you know, similar type things. And that like all of that is useful and true when it returns this is infeasible. It gets a lot more difficult if it just runs out of time, right? You're kind of left, the best answer I have is like, go put on your thinking cap, right? Like I don't know, every single one of those cases has been a different kind of failure. Another very tricky thing when you're doing PDDL or task planning in general is like, how do you pick the right level of abstraction, right? Like I feel like I've been thinking about this problem for a long time because it was part of my thesis work, and still, even when I'm trying to do it by hand, I still struggle with, you know, where do we want to put that layer of abstraction? So here's one example that is bad in one direction. This is the robot cutting a piece of lumber. The symbolic action for that, we call it get and cut lumber. It goes over to the bunk, picks up a piece of lumber, puts it into the input table, cuts it. The downside there is that if it fails anywhere in that symbolic state, you lose all of that. And you got to go all the way back to the beginning. So maybe we want to think about reentrant symbolic things, right, where our preconditions can be kind of sort of satisfied or change over time. The benefit of that is, you know, our task plan ends up being shorter. On the, you know, kind of on the other side is, here's our tool belt. We've got a bunch of tools. We have a symbolic action for just picking up tools. The downside is that there's actually like 3 or 4 things that you have to do to pick up a tool. They're relatively simple things, but you always have to do that order of things. And so it actually makes the task planner's job a lot more difficult because you're extending the depth of the correct path, right? And so there's this kind of trade-off where you have to think about what's the right way to break it up, so that way when you're executing, you're losing as little state as possible, and then when you're planning, you know, there's kind of this trade-off of can you make it easier to plan. So those are kind of my insights. We're hiring. We're based in Durham, North Carolina. We need senior mechanical engineers, senior software engineers, firmware engineers, robot generalists. I know you're out there. Any questions?
Let's think. If anyone has a question, please queue at the microphone. And Federico, you can go ahead.
I'm the first on queue. So thank you. Great presentation. Don't know if this is working, but you can hear me.
Yep.
Two quick questions. Number one, is there any parallelism in your plans? Since you're using fast downward, even if there is, I guess you're not exploiting it.
Yeah, there is currently no parallelism in the plans. Asynchronous execution of both arms is on the roadmap, but not implemented yet.
Okay. And then second, have you thought of, or have you looked into hierarchical representations like HTN or similar?
Yeah, I'm vaguely aware of them, but have not dug into them. They do kind of seem like maybe an interesting solution to picking the right abstraction layer.
Right, and maybe would help you in the process of deciding that level of abstraction,
Right.
and going between levels of abstraction, which might help also at execution time.
Yeah.
Maybe HTN Planning in the Now, which is a paper from a few years ago. I can give you details later.
Okay.
That might be an interesting paper.
That'd be wonderful. Thank you.
More questions?
Thank you very much for your wonderful presentation. Maybe I have a question beyond the motion plannings. As you know, we are entering an age of massive customization, especially in the construction areas. If we want to build different houses, we need different floors. So the notion of flexible manufacturing has been, the hotly studied in the academia. But I want to hear your opinion in the industry. What do you think are the challenges of this flexible manufacturing, and are you considering it as the future development direction?
So the only reason we're doing task and motion planning is because we have to be flexible, right? We've built 9 homes so far. Every single one of them is different. If you think about housing in general or mass customization, right? It's the most copied house ever had 1,000 copies, right? Like my GM Bolt has 17,000 brothers and sisters, right? Like so it's just a totally different layer, and to get into it, you have to be flexible, right? Not only from a design standpoint, but every piece of wood is different. They're all bowed and twisted and knotted in their own special ways. And you have to address that specifically.
I see. Thank you.
One final quick question, if anyone wants to go.
Yeah, thanks for a very interesting talk. I'm wondering, let's say you do the task and motion planning and you have people do the assembly. Is it still faster than doing it with a robot?
Right now, it depends on the time of day.
Okay.
So first thing in the
For
morning,
humans,
they
or-
are kicking our pants. They are very fast in the morning, right after their coffee. After lunch, more of a horse race. We're also operating the robots very slowly right now. I didn't want to crash $150,000 robots. So we're at like 20-ish% on robot speed. So there's kind of an easy button of just like dial it up, and then it'll pretty much always be competitive or faster.
And maybe a follow-up question to this, to your answer to the previous person who asked the question. You said like all these woods are like twisted and have like these, all these different structures. And I'm wondering, if you look at the overall problem space, like is perception still a problem and the execution under these conditions? Or is it, would you say like that's not kind of, we got that under control, we kind of know how to do it? Or
Yeah,
how do you think about
our perception from our last house build is pretty rock solid. At least for, like, the nice thing is we own this environment, right? So it's kind of easy for us to design a work table in a work environment where perception's really easy. So, you know, of the things that I worry about, perception isn't one of them anymore. Cool.
All right. Well,
Thank you.
Thank you, Barrett, for a very interesting and different talk. I think it was very interesting perspective, and this is why we had this workshop. So thank you for coming.